Now we will see how to plot the polar plot for a special case transfer functions. If at all, if the transfer function is a non-minimum phase transfer function or open loop unstable transfer function, so we can call them as special cases, and how to treat those special cases using the polar plot. We know that we can draw the polar plots of systems, but we cannot apply the concept of gain margin, phase margin to find the closed loop system stability. Whereas this polar plot can be used in Nyquist plot, and Nyquist plot stability criterion is the absolute stability and relative stability of the system. Now, how to plot the polar plot, this kind of open loop transfer functions. Now we know that whenever you have transfer functions like 1 minus s or s minus 1, then its magnitude and phase angles will be different from s plus 1 or s plus 2 or 1 plus 2s or 1 plus 3s. Now, so if at all, if I have the phase angle like this for the components which we have, the angle of a plus or minus jb. So if you have a plus or minus jb, it will be plus or minus tan inverse b by a. Plus or minus tan inverse b by a if you have a plus or minus jb. Now, if at all minus of a plus or minus jb. So this minus indicates, the minus 1 indicates 180 degrees. So that is equal to 180 plus or minus tan inverse of b by a. I need to introduce 180 degrees to take care about the minus. So when you elaborate, it will be something like this: phase angle of a plus jb, which is well known to us, tan inverse of b by a. Whenever you have a minus jb, then tan inverse it is minus tan inverse b by a. And similarly, third one, let us take minus a minus b, that is going to be tan in 180 plus tan inverse b by a. Then the last one is minus a plus jb, that is nothing but 180 minus tan inverse b by a. So these are the formulas used whenever you write the phase angle expression for the open loop transfer function. What are the steps to be followed? There is only change in the phase angle expression, the remaining steps are same. So whenever the open loop transfer function is given, substitute s is equal j omega, get gh of j omega, and write the magnitude and phase angle expressions. Once you have the magnitude, phase angle, while writing the phase angle expression, we have to take care about the previous one. Now, so again I am going to prepare the table where there are again 4 entries needed. So what are the 4 entries? For omega value 0, infinity, and also there is a point nearer to the 0, there is a point nearer to the infinity. For these omega values, what is the magnitude and what is the phase angle? So we cannot directly write the phase angle, the starting phase angle and ending phase angle, because this is special cases. So we have to look at the phase angle expression, we need to substitute the omega value there, then only we can get what is phi naught and phi infinity, similarly what is m naught and m infinity. Now let us take one example. The open loop transfer function gh of s is equal to k into s plus 1 divided by 1 minus s. The open loop transfer function is k into s plus 1 by 1 minus s. Since we have 1 minus s, which indicates it's a special case, then write what is gh of j omega. Gh of j omega is k as it is, 1 plus j omega divided by 1 minus j omega. The magnitude is k into under root 1 plus omega square upon under root 1 plus omega square. So magnitude numerator denominator same, the remaining is k. That means the magnitude of this particular transfer function is always k. The magnitude is k. Now next is phase angle. How to write the phase angle? Now whenever you have special cases, phase angle expression is very important. So numerator I can write it as tan inverse omega. The denominator I have 1 minus s. So what you have written it as 1 minus j omega. So it is type of a minus jb. Then we can write it as the respective phase angle as minus tan inverse b by a. So when it comes here, then it is going to be tan inverse omega already, which you have written, minus of minus tan inverse omega. The result is 2 tan inverse omega. So 2 tan inverse omega is the phase angle expression for the given open loop transfer function. Now look at the table how we can prepare it. When omega is 0, the magnitude is k, because all the values of k only, because magnitude is independent of frequency in this case. What is the phase angle? The phase angle is going to be 0, and again when omega is infinity, it is going to be 180 degrees. So 0 to 180 degrees it is going to vary. But when it is varying, what are the in between values? So we have all positive values. When omega is 0.01, it is going to be plus 1.16. When omega is nearer to the infinity, let us say 10,000, it is going to be minus 179 plus 179.9. So I have plus value here, plus value here. Then how to sketch this? So when you draw the polar plot, look at this, and it is a type 0 system. So generally whenever you have type 0 system, there will be a point. But we cannot say that the point is always in the 0 degree line, since we have special cases. So this point can be either on the 0 degree line or 180 degrees line. Now in this case, the starting point magnitude is k and phase angle is 0 degrees. Therefore from the origin, then I can take k distance and on 0 degree line locate the point. That is the starting point, omega is 0. The ending point is also, I have magnitude k, the phase angle is 180 degrees. So plus 180 minus 180 is the same line, because when you measure clockwise you will be reaching 180 degrees, that is minus. When you measure anti-clockwise, again you are reaching minus 180 degrees plus. So plus minus will be the same line. So 180 degrees again k. So in this line you take the k and measure the k and locate the point. Starting point there, ending point here. Then what I need to do? I need to take a plot like this. But which one you should take? There are two possibilities. I can start here, then I can come like this, which is a clockwise direction, and I can also take the anti-clockwise. Since all my angles are positive, then you will be having anti-clockwise direction of the polar plot. So this is the polar plot for this particular system.